And welcome to this session today on lights, lens, and logic, where we're going to look at how we can create embedded imaging solutions in AMD FPGAs. If somebody could just drop in the chat, just let me know that you can all hear me okay and that you can see me, and then we'll make a start on it soon. So for everybody that wants to watch this or doesn't or is running a little bit late, we will be recording this and it'll be available, and all of the slides and the demos and everything will also be available via my GitHub. So today what we're going to do is we're going to take a look at creating an image processing project, and it's a little funny actually because I was working with somebody early on this morning. I had a meeting and I was trying to categorize my Hackster projects, and I realized that actually a lot of my Hackster projects are image processing projects, which is quite interesting. And then I had a lot of fun preparing for this afternoon, because I've been preparing the demo to make sure that the demo is all up and running. I'll show you the demo in a minute for a really good reason. But I've been preparing this demo and I turned it on. And I did this weeks ago. I turned it on and I'm like, this should work, and nothing came to life, and I was like, "Ooh, this is not very good." So about 5 minutes ago, as I was beginning to panic a little bit, I realized that actually the USB cable that was plugged into the camera was turning it off and putting it into a memory card mode. And it wasn't actually outputting any video, so that's good. So today we're going to take a look and we're going to work on how to get this system up and running. So we've got a Kintex FPGA here. We've got a HDMI camera coming in. HDMI camera coming out, and as you can see, the screen is responsive and is working. And I'll just tilt that back down again so you can actually you'll actually see me. So we're going to take a look at how we can do that, and we're going to take a little bit of a look beforehand at some of the key elements of image processing and how we can do it. All of the instructions for this will be available at the link below, as well as the GitHub is also just here, and I will put the slides up as well from today. So as we go through this, any questions, please just jump out and shout and pop them in the chat. I'll keep my eyes on the chat as well, and we'll see what we can do, and we'll answer them. So like I say, as we go through it, just let us know. So let's take a start now. So for anybody that doesn't have my email address and thinks of any questions afterwards, then you can get my email address there, and away we can go. So our session objectives today is we're going to take a look at a few things, rather than just telling you how to create the image processing pipeline using Vivado and Vitus. We're going to take a little bit of a look at the holistic overview of generally how do image sensors work, what are the image sensor types that we could have, the different types of interfacing that we might have. And I've got one demo set up, but if we get time, I might be able to squeeze in another, and then very importantly, we're going to take a look at the FPGA architecture and IP and how we can use this. Now, the architecture is very, very important actually, because if you remember, I said that I was trying to get the demo up and running, and it wasn't working. You know, there was nothing coming out of the HDMI screen, and then I remembered why it is. That's actually due to how I chose to make the architecture, how I chose to implement the architecture. And perhaps if I'd not been running about so much this afternoon, I would have remembered that slightly before I'd rebuilt the project a couple of times, trying to fix issues that were non-existent. And then once we've done that, we will jump into our image processing example, and we'll take a look there. So one of the cool things about image sensors actually is they allow us really to see how we interpret the world. So they allow us to see the visible spectrum, but they also allow us to see much wider than that. So when I think about my career as an engineer, as an electronic engineer, as an FPGA engineer, I've designed image-based systems that work in the infrared. Actually, infrared was the first time I ever designed any image processing systems. It was a thermal imaging camera. was the first one I ever designed. It was also the first time I came across what would then be turned into AI, and that was in around 2006, 2007. So that's really cool, Cornelius, working on a X-ray spectrometer satellite, and we can obviously we can do the same at the other end. We can capture X-rays using, provided we use the right image, sensor, then we can do that. Although some of these things, it might actually, over time, it might actually begin to damage the image sensor as well. So not only that's the great thing about image processing. Not only can we see a work and process within the visible spectrum, but we can also go out to the infrared and to the X-ray spectrum as well, which is one of the things that I really like about it. And when it comes to this, there's actually a couple of technologies that we generally use. There's some more very specific technologies that are generally used for infrared, where you need slightly different semiconductor physics to be able to ensure that the photons can cross the band gap and etc. But by and large, if we're working from the visible spectrum, or maybe just a little bit into the IR spectrum, all the way up to the sort of the X-ray side of things, then we're going to be using either a charge coupled device, which is a CCD, or a CMOS imaging device. And the little board on the side, I have one just here. The little board on the side we have is one of the boards we developed, and this is actually an imaging board for the microZ. So you can plug the microZ into the back of it, and there's a CMOS image sensor on the front, and there's a HDMI set output on the side. A cool little project for image sensing. When it comes to working out which one of these image sensors that we want to use, there's a lot of choices, there's a lot of options in buying the image sensor. One of these becomes whether we want to look at the performance and how good a performance do we want from the image sensor. So obviously one of these performance metrics that's very important for an image sensor is the quantum efficiency. And that's basically just the ratio of photons striking the device versus the photons that are actually detected in the actual pixel. Now, obviously, these devices are built in semiconductors. And what happens is, depending upon the side we illuminate the image sensor from, it will have a really big impact on the quantum efficiency. So if we have what's called a front illuminated device, where all of the pixels, everything's been built up on top of the device. If we use that side as the illumination source, so that's where all the photons hit, then there are metallization layers, there are structures within this image sensor itself that the photons will strike, and they will reflect off, and they will not be collected then in the pixel. The alternative approach is to actually have a back illuminated device where you use chemical mechanical polishing to reduce the silicon on the back of the image sensor and let the photons come in from the back. So you don't have all the metallization layers, all of the structures on the silicon that might that might cause reflections for the photons. And by doing that, you get a much higher quantum efficiency. Of course, because there's more processes involved, and actually there's quite a bit of risk in doing the backfitting, as they call it. Then the cost for those devices are quite increased. But it's very important to be able to understand whether we want a front illuminated device or a back illuminated device, depending upon which type of the quantum efficiency and the performance that we want. Now, one of the really cool things about image sensors actually is we generally think of the 2D array to actually take and create a picture. And just as I showed with the image sensor earlier on, that's a 2D sensor. Normally, when we take an image, we want to grab that 2D image, and we take it by having a 2D array and doing a snapshot of storing all of the charge in the photons in the pixels at any one point in time. We can do this, however, by having a single row of pixels and moving the image past it. So a common approach to this is if you're on a conveyor belt, you could recreate a two-dimensional image by having a line scan camera, and as the object moves past, it builds a two-dimensional image. This is also quite popular in space applications as well, where you have a satellite with a large array on it, a large line scan type array, and the rotation of the satellite around the Earth causes the rotation and creates that two-dimensional image. And you're exactly right. So NASA, you're right as you said that, you know, phased array radar will do it as well. And Cornelius, I bet your satellite that's got a bank of backlit CCDs, I would hazard a bet that they were made by Teledyne E2V, which is a company actually that taught me a lot about this, because I used to be Teledyne E2V's chief engineer for space imaging for a couple of years. The other interesting thing that we like about image sensors is how we actually read out the image. And you'll all have seen the great things that you can see online, and actually in the project, I've not put it in the presentation, but in the project there's a great link to this, where there's a helicopter taking off, and its rotor blades don't appear to be moving at all. And the reason its rotor blades aren't moving at all is the image sensor that's capturing the image is what's called a rolling shutter image. So that's reading out a line at a time from the sensor. It's not reading all of the pixels out at once. It's currently reading a line out at a time. And what that means is that it's possible to get in synchronization with events, and that's exactly what happens with things when helicopters appear to levitate and such like. It gets all synced up with the rolling shutter, and it's read out. And that can cause not only those synchronization events, but it can also cause corruption due to the movement, because there might be some movement or change between one line and the next. The other one, obviously, is to take a global shutter approach, and in that case, we take the global shutter and we take every pixel that's in there after its integration time and read it out. Again, generally the costs and the prices depend upon which option you take. Once we've selected our image sensor, and this is one of the things that you kind of learn once you start doing a lot of image processing, actually, in that we need to think about whether we want our image sensor to work in the color scale or to work in the grayscale. What's interesting, actually, as you start doing a lot of image processing, is you realize that a lot of these applications use a grayscale image. So a lot of image processing might even use an RGB camera, for example, a HDMI camera, like in this example, and then it will convert it to a grayscale image before it does the other processing. And as you'll see when we talk about why we do that in a minute in the FPGA, it can have a significant impact and improvement, particularly in performance, by doing that, by moving it into the grayscale. So if we've got a grayscale image, obviously we've got the luminance information, so we can see areas of brightness, we can see contrast, we can see edge, shapes, textures, perspectives, and we can see a lot of information there without requiring color. And because these grayscale images only convey the luminance of the image until we start doing some other interesting processing with it, it means that we can transfer the pixel data with many fewer bits. So we can have a much reduced number of bits to transfer the image, which means we can fly that through the FPGA faster. If we're buffering things within the FPGA, we need less memory, and it reduces overall the complexity of doing any calculations on it, because we're only working with one channel, which is the luminance channel. So it's a very, very powerful thing, actually. And in a lot of applications, you'll see that we first get the image, maybe a color image, and one of the first things we'll do is translate it to into a grayscale image, such that we can reduce the amount of processing that needs to be done. Now, if we want to work with a color solution, a color image, obviously our image sensor, it's just got an array of pixels on it. And those pixels, they just accumulate every wavelength of light going. So they will accumulate the reds, the greens, the blues, and everything. So what we need to do is we need to put on what's called an optical filter, which is commonly known as a Bayer mask, on top of the image sensor. And what that does is it means that only one wavelength is allowed through into that pixel. So for example, if we've got a pixel, we've got a mask on top of it, that pixel will only collect red photons or green photons or blue photons. And typically what happens then is we collect these photons in the pixels. We collect them normally in groups of 4. And normally those groups of 4 are the 2 bottom pixels and then the 2 top pixels. So if you can see my mouse here, you'll see that we have a red, a blue, and 2 green pixels. And we will use this quad of pixels here in our image processing stage to convert into a full color pixel for each of the 4 pixels. Now, the reason that we use 2 green, but only 1 red and 1 blue is our eyes are actually much more sensitive to the green wavelength, because we've got red at one side of the spectrum, we've got blue at the other. So green sits slap bang in the middle of our visual spectrum. So we're much more tuned to that. So we have two green, 1 red and 1 blue. What this means then is that within our FPGA, and as we begin to think about how we implement this within our FPGA, we have to think about the color space and how we're going to move this information. So typically what will happen is if we're working with a grayscale imager, or we're working with the raw pixel value that's got a Bayer mask on top of it, we will get an 8 or a 10 or a 12-bit pixel value. Now, if that's a grayscale picture, then we will just keep using that 8, 10, or 12-bit pixel as we want in our processing chain. If, however, we want to convert that into a color pixel, what will happen is we will put this through a de-Bayer mask or a de-Bayer processing stage within the FPGA. What this will do is it will convert this 1 pixel into a pixel that has 3 color channels within it. So it will be, for example, if we have an 8-bit raw format, we will end up with a 24-bit pixel. So we will end up with 8 bits for the red, 8 bits for the blue, 8 bits for the green. If we have a 10-bit raw format, we will end up with 10 bits, 10 bits, and 10 bits, a 32-bit. And if we have 12 bits, then we will end up with 12 bits, 12 bits, and 12 bits. Now, this is interesting because within our FPGA, obviously, we're going to be using this within a stream of pixels. We're going to be using AXI streams. We're going to be using AXI memory maps when we want to store this into the memory map. So we need to think about how efficiently 24-bit pixels go into a 32-bit system, generally into memory or not, which the answer is not too well. So what we might want to do is we might want to change the color space, and we might want to convert from RGB, which uses 24 bits per pixel, and we might want to convert into a YUV scheme, where again there's 22 bits, there's 24 bits of pixel if we use a 444 with 8 bits per channel, so 8 bits for the luminance, and then the 2 chrominance channels. But actually, what we can do with YUV color scheme is we can keep updating the luminance channel, and we can share the Y and the U elements between 2 pixels. So that allows us to store a 16-bit pixel, which when we're working on our FPGA, when we're routing data around, actually in modern FPGAs, it's not too much of a problem. But when we're storing data in DDR memory, for example, if we're doing a frame buffer, as you'll see when we come to it, that might actually makes a big difference in how we can pack that data and store that data within the memory that we have on the system. So this is where we begin to look at the FPGA. Having looked a little bit at image processing, the sensors and what they are, and a few key aspects to understand around them. It takes time now to take a look at some of the interfacing with FPGAs, and we have 2 direct ways we can do this. And if you've ever been to my office, you know, if anybody's over in the UK and they want to come meet me, you know, give us a shout. You can come and take a look around. You'll notice one thing is we've got lots of cameras and demos just scattered around the place. Most of them that are doing image processing. And we have this little one down here, which is the in the image. It is a Trends copy of the Pi Zero, I think, which has got a little zinc FPGA on it. I think that might hold the record for the longest FPGA design that I've had up and running continuously, because it's been sat on my desk just to the left of me for a good 2 or 3 years now, and I've never turned it off. And that's a great example of how we might want to interface with the sensors, because what we typically get is we get options in the FPGA. Do we want to interface directly with the camera using some interface such as MIPI, as is demonstrated in this example? And in that instance, we have to configure this set. We have to power up the sensor, configure the sensor. We have to write software to drive and get that sensor into the right format. And then we have to receive the MIPI video and process it in an image processing pipeline. The other approach is that we could be working with a camera, like in the demonstration I showed earlier on. What's connected to that is a little GoPro type camera, and into that we don't have to do any configuration or anything. We can just turn it on, and provided you've got the USB correct and you've not put it in some sort of mass memory mode, then what happens is you can pull it through and it will just output HDMI video all day. So all we need to do in our image processing system then is grab that HDMI video and process it through. So when we're working with FPGAs, we get two distinct choices, whether we're going to be working with integrating the camera, the sensor directly itself, or interfacing directly with a camera. And there's a few different interface standards that we've worked with over the years with our FPGAs. HDMI obviously is one of the most common ones for working with cameras. We also do a lot of SDI, so serial digital interface video. So SDI video, so 3G SDI, 12G SDI, and that comes down, and that's really quite nice to work with, because it just comes down a coax and into some sort of transceiver, and we can pull that out. HDMI, generally, depending upon what the format is, it's either going into a coax and going into one of the GTs, or it's coming into the pins individually, because they can support TMDS, which is what HDMI uses. Camera Link's an interesting interface, because you generally think that Camera Link's quite an old interface and it's not something that's not used too often. But actually, we see Camera Link quite a lot, particularly in sort of systems and applications where we've got, say, thermal imaging or high-end sort of defense type cameras and such like. One of the more popular ones as well that we see in a lot of applications, for example, the sensor I was just talking about, or the example that's behind me connected to the Versal demo, is a MIPI camera. So MIPI is a mobile industry processor interface, and it's only really designed for going about 30 centimeters, so maybe 30 centimeters or so. It's not really designed for going over long runs. You can make it go over long runs with things like GMSL, which take the MIPI, convert it into a coax, and then take the coax and then convert it into a MIPI again for connection to the FPGA. And that's really popular in like the automotive, the aerospace, the defense type applications. And then, as you'll see when we do the demo, there's also a range of sort of traditional parallel serial interfaces that we can use and come to that, as you'll see when we go through. So Harish, some of these specs are open, some of these specs aren't. So I don't think the HDMI specs are open. I think that's closed. I'm not sure about SDI. Camera Link is fairly open. MIPI again is semi-open, I would say. In the parallel and serial, that changes them all. Deepak, if you want to download this, I'll put a link out. Keep an eye on my website and my LinkedIn, and there will be a lot. I don't know, Rocco, why camera link is used so much in the thermal imaging cameras. I think it's just a very popular industrial sort of standard. There's a lot of camera link frame grabbing boards available in PCs as well, so maybe that's one of the reasons that they go with it. But once we get into our FPGA, as we'll see, one of the things we want to be able to do is transfer the data from image processing element to image processing element. And this is where one of the benefits of the FPGA comes in, because we can literally stream data from one block to the other to another processing block and have them going in parallel. So typically when we do this in an FPGA, what we want to do is we want to use what's called the AXI stream protocol. An AXI stream, it gives us basically a data, a valid, and a ready signal. And that allows us to send a stream of data through, which is ideal for pixels because we could just send a stream of pixels through forever and a day. However, at some point, we do need to know where a new frame is starting and when a line is completed or a line is about to end, because we need to be able to reconstruct the 2D image. So we can use the sideband signals within the image, within the AXI standard, to give us that timing information. So we can use the T user signal to indicate when we have a new frame, the start of a new frame. So when a new frame starts, we pulse T user with the first pixel. When the line ends, we can pulse T last to tell us that that's the end of the line. And knowing the start position of the frame and knowing when the line ends, we can reconstitute, if we need, a two-dimensional image, or we can process, as you'll see when we do when we talk about image processing in a second, we can store and buffer lines in block RAMs and FIFOs and such like as part of our image processing application. Skipping ahead one too many there. So one of the things that we want to do with our system is we want to get the throughput as fast as possible within the FPGA. So what we could see previously on the previous slide was we were transferring 1 pixel per clock, and that means, so if we've got a 720p image, we've got 1280 clocks to send all the pixels. However, if we have multiple pixels per clock, we can send multiple pixels on every clock. And this is one of the benefits of the FPGA, because we can have as wide a buses as we want inside the FPGA. So we can have maybe 1 pixel per clock. Yeah, that's okay, but it's fairly slow. We could have 2 pixels per clock, 4 pixels per clock, or 8 pixels per clock, and do them all and transfer these pixels in parallel. That really increases the frame rate of the FPGA that we can support, and the data processing and the data throughput. Now, one of the key things to do this, and we're going to talk about IP blocks in a minute, is that we need to make sure, if we're going to have an image processing chain, we're going to try to, or we should try to, use as many IP blocks from the library as possible. And we need to make sure that all of those IP blocks support the pixels per clock that you expect. So some might only support 4 or 8 or 2. So you have to make sure that the entire processing chain, up until you do something, i.e. put it in DMA or take it out of DMA, is able to support that. Jose, I will answer your question in a minute about the video for Linux and sending it through the FPGA. So this pixels per clock is really important, because it allows us to get that throughput. And a few years ago, we did some image processing where and I should have put this slide in actually. We did some image processing where we needed to be able to do thousands of images, thousands of frames per second, actually tens of thousands per frames per second. And it was really impressive just to see how big a difference it would have by changing the number of pixels per clock on that throughput as we were running through. So we understand a little bit now about that image processing pipeline, the how we're going to transfer data in our FPGA. So we understand that we can use AXI stream, we can have multiple pixels per clock. What we need to think about now is how are we going to do this? So do we want a fairly responsive architecture, or do we want one where there might be some delays or some buffering in it? So one thing I've called the direct architecture, and I had to think of a name for it, so I called it direct in this instance, is where the input is connected to the input processing is connected to the output processing, and obviously through the processing algorithms. What this means is that there's very little buffering between the input and the output. So there's no frame buffer where an entire frame or multiple frames are stored in DDR memory and they're read in and then they're read out. What this means is that as the input pixels come in, they're being processed on the fly and they're being put on the output. Now, this gives you a very minimal latency between input to output. So this is very useful if you're doing anything where you need to interact with your environment in real time. For example, if you were driving a vehicle, you might, and you were solely reliant on the cameras driving the vehicle, you would want to make sure that the delay was as minimal as possible. So you would go through something like this. It has some great advantages because it's exceptionally fast to get through. But we need to be careful about how we process that frame, and any sort of issue on the front end, for example, will stall the image processing pipeline and result in there being no image being put on the output, because there's nothing to feed the pipe, shall we say, and there's no buffer of memory in there that sort of puts out the image. That's exactly in that demo today. The demo that I showed you earlier on, the live example of it working on my desk, and what's shown in the Light Lens Logic Hackster project, that's exactly what we've implemented. We've implemented that direct architecture, that just passing straight through from one to the next stage, and it works really well. Now, there's another element which actually comes into a little bit of what Jose was just asking about his question, in where we implement a frame buffer in this architecture. And in there, we might have the input processing, we might have some initial processing algorithms. We then use a VDMA, a video direct memory access, to write the AXI stream into some DDR, either DDR3, DDR4, DDR5, whatever. If we're working with a Zinc or ZencMP or a Versal, this is also going to be sat within the processor memory. And that's where, if you're doing any video for Linux, the processor might pick it up and begin to use it. Having this means that we can manipulate the image in the processor, in the soft processing world. So if you're doing, for example, CNNs, image-based processing, this is quite important, because you've got to get the image into some sort of memory mapped space. Or if you've got a different size output to input, so for example, you've got a 1280p input, but you've got a HD output, a 1920 output, because you're going to put some additional information surrounding the image as information around that. So you would have different input timing and different output timing. So you would need to be able to generate that and get that going correctly, such that the input and the output are decoupled by this frame buffer. And actually, by and large, if you look at the projects I've done over the years, most of them actually have been using this architecture. Most of them have gone through this decoupled frame buffer type architecture, because it's the one that allows us to experiment a little bit more with it. But it's a very useful thing. And working out which one you want to do, whether you want to do a direct or whether you want to do a frame buffered one, it really depends upon your application. And the idea today, with the demo today and what we've been talking about today, is to give you an understanding of how to do that, give you a reference design of how to do that. There's a reference Bravado design available on the GitHub that I linked earlier on, that you can go and get and take through. And then you can start working on it yourself. And if you want to, I mean, we're just doing a simple pass through for this example, but if you want to, you can start adding in examples that you want, elements that you want, image processing elements, and such like. Now, which leads us nicely to talking about how we might do image processing algorithms. And perhaps one of the most common ways to do this is to have a sliding window. So we will slide a 3x3 or a 5x5 or a 7x7 matrix over the pixels in the image, and that could have those pixels. We could be sliding over those pixels and doing something like a median order filter, or we could be applying weights to those pixels. So what we do essentially is we use the surrounding pixels here, so that the red pixels here. For example, if we're working on pixel 10, so we work on the pixel in the middle. So we work on pixel 10. We would be applying values to all these other pixels surrounding it. A value to pixel 10, doing some sort of summation, and then giving a new value for pixel 10. And this can be used to do things such as Sobel filtering, convolutional filtering, reducing noise in the image, adding noise in the image, I guess, if you wanted to. So a lot of the fundamental elements of image processing are based around this sliding window approach. And obviously, I cheated a little bit when I drew this, because I drew this such that the pixel would be in the middle here. Obviously, when you start out, you have to be very careful about how you have to consider how you go around the edges of the image where the pixel doesn't quite fit. So this is just a nice example of what I was just trying to explain. We might have a number of pixels in a 3x3 array. We would have 9 pixels, obviously, and then we might have, depending upon what function we're doing, we would have a number of weights that we might want to multiply that pixel by. They might be binary weights, they might be 0, they might be 1, they might be fractional, and then we'll do a summation to create the new pixel value. This is another area where FPGAs are very good at this, because the FPGA obviously is excellent at fixed point maths. And if you're not too familiar with fixed point maths, there's a great fixed point maths project on my Hackster. So you can run that fixed point maths and actually easily in the FPGA get a nice fast result. So the FPGA is doing its maths, it's doing the multiplication, it's doing the addition, it's doing the summation. It's all running in parallel, but it's all fixed point. It's all just simple logic gates. So you can still maintain the throughput that you want to maintain going through. Maybe be it 30 frames per second, 60 frames per second, 100 frames per second, 200 frames per second, or faster. And an example here, if we wanted to create that example, then what we should do when it comes to creating algorithms really is we should really try wherever possible to try and leverage existing IP. I guess I'm quite a lazy engineer. I like thinking of the solution and how to do it. The implementation, always I get a bit bored about midway through the implementation. So that's one of the things that we want to do, is try and leverage the IP wherever possible. When we're working with AMD FPGAs, obviously that IP is available in a lot of places. We can get that from the Vivado, as we'll see. We can get that from the Vitis Vision library, which has got literally a load of OpenCV type functions in C that we can use and we can put into the hardware. We can use Model Composer, or we could use third-party tools like MATLAB and Simulink. And I'm quite a big fan of using those if you've followed me for a while. So Vivado's got a nice range of IP. In fact, Vivado gives us everything you need to create an image processing chain, from getting a sensor in to getting an image out on a screen. Vivado is going to give us all of that basic infrastructure. It's not really going to give us anything that's hugely algorithmically that we might want to put in, like median filters or convolutional filters or things like that. But it will give us everything that we want to do in that aspect, to just do that basic image processing pipeline. And everything in the example you see in GitHub is brought from using those IP cores. If we want to get more advanced and start taking a look at more advanced IP cores that we can generate and we can drop in there, then the Vitis Vision library has literally tens, maybe even hundreds of components that can be synthesized and dropped into your design or used into your design that are equivalent to the functions that are made in OpenCV. So we can, ideally they're intended for use with the Vitis system designer, system builder approach, but the level 1 IPs, the basic building blocks, you can actually take that and you can actually synthesize that and turn that into an IP block that you can pull into your Vivado project and use there. So instead of you having to write the function that you need, you can just pull it from the Vivado Vision, the Vitis Vision library, and do a little bit of HLS synthesis. And if that interests anybody, I'll create some projects and some blogs on how to do that, because that's quite cool. Model Composer is very similar. It gives us some features and the ability to use sort of in collaboration with MATLAB and Simulink. It gives us that ability to create filters and elements that we could drop into our design, because it creates as an IP block that we can pop into our Vivado solution. What's cool is if you use Inversal, then you can use a lot of these. You can target a lot of these functions actually into the AI engines and use them for DSP as well. So that's quite cool. And then if you want to do anything with sort of like third-party stuff, you know, the MATLAB Simulink, actually, we use quite a lot of this in our image processing applications. We can use MATLAB Simulink, and we can develop the algorithm and drop it into the FPGA as an IP core as part of that image processing pipeline. And here, there's a simple example that we dropped and deployed into the AC701 in that example, which was a median filter. And we've done several of these. We've done a lot of these actually based around the 106 for a client. We've done a lot of image processing based around that 106 and using MATLAB and Simulink. But let's take a look quickly. I've talked for way longer than I intended to, but let's take a look quickly at the design that we have for the demo, and then we'll come back and see if there's any questions. So hopefully everybody can see that. Let me pop that out of Vivado a little bit. We'll make that into a bigger screen so as it looks like everybody can see it a little bit there. So what we have here is we have the selection of the demo that we saw earlier on. So everything in this demo, everything that's running on the demo is reflected in this Vivado project. The key elements here, although we don't use it as a frame buffer. Excuse me, we don't use it as a frame buffer, but we have a DDR MIG, and we use the DDR MIG actually to provide us some clocks that we want, and to provide us the user clock that we're going to clock the Microblaze RISC-V at. The reason I added the MIG is I want to do some more software development on this, and some more software functionality, and that won't be able to fit within the VRAM that's available to the Microblaze. So by having the DDR, we can execute the program in DDR and run it. We then have the RISC-V Microblaze. I don't know who's tried this. So the MIG, sorry Cornelius, the MIG is the memory interface generator. And that generates a DDR, so there's DDR3 on the board, and the MIG generates a DDR3 interface. So it generates all of the DDR timings and everything for that device that's fitted, for all the devices that are fitted on the board. And it just gives us a simple AXI interface such that we can read and write from it. I don't know how many people have tried the RISC-V Microblaze, the Microblaze V. But this is like now one of my favorite elements in the design, and we're going to use this. Basically, we use this RISC-V to configure the image processing stages and to make sure that we've got the image processing stages correctly configured. I've configured this one as a microcontroller preset. I'm not too worried about the performance of it because it's not part of the image processing chain. it's just doing the setup. But I do want to make sure that I have lots of logic available in the future for adding in processing IP on the image processing chain. So I've set the optimization in this instance to a area optimization. I've left pretty much all of the defaults unchanged. The only major change, I think, is I have enabled the AXI instruction interface as well. So David, that's a good question. It's not going to consume too much resources of the FPGA, and I will let you know in a minute once we've pulled it through. But it's quite a nice little system. Obviously, we've then got the debug, the Microblaze debug module there. So the RISC-free Microblaze, it's available in, I think it was 2023.2, maybe. It's certainly available in 2024.1. 2024.2 and 2025.1, which is upcoming. So it's all there and available, and it's just the new version of the Microblaze. At the moment, it supports only microcontroller and real time with an application one coming soon. Yes, it will support DDR. It will support DDR4, and some of them will support some of the upcoming ones, like I think the Spartan Ultrascale Plus. And particularly Versal, they support, some versions of Versal, they support DDR5. So we've got a relatively small, it looks large on the diagram, we've got a relatively small image microprocessor controlling system. I've got a UART for reporting, and then I've got a GPIO. And the role of the GPIO is to drive the hot plug detect on the HDMI camera. That's its entire role. It's going to be software controlled. As the software's gone through and it's ready to start receiving the image, it's going to drive the hot plug detect such that the camera starts outputting its data via the HDMI and not via the screen that's on the back of the camera. So then we have what I've pulled together into this block and said this is the image processing block. So if we take a look in that image processing block by double clicking on it, we'll just pop that out again. Next time we'll do a live build and see if we can get one up and running in a live build, because that's quite exciting. But what we'll see here is quite interesting. I'm going to move the blocks about a little bit just to make it a little bit simpler to everyone. So we have hopefully that's going to sit there. So we have the first stage that comes in from the HDMI. We have the HDMI input, and we have a DVI to RGB converter. So this converts the incoming signals from the camera into a parallel format of video. So this is going to give us a 23-bit pixel because it's a color pixel. It's going to give us horizontal syncs, vertical syncs, and when the video is active. So this is going to give us a very old-fashioned type of parallel video going through. It's also going to give us a pixel clock that's recovered from the HDMI. Now, I want to be able to work with this in AXI streaming, as I said, because AXI stream makes it nice and easy, and all the infrastructure is built around that. So I've then added in this block here, the video in to AXI for stream. What this module does is it takes the parallel video that's come in, the 23-bit parallel video, the horizontal sync, the vertical sync, and the pixel ready sync, and the pixel enabled signal, and it converts it into that AXI stream of pixels. So if you take a look at the video out, you'll see we've got a T data, we've got a 24-bit pixel because it's 1 pixel per clock. We've got the T last, we've got the ready, we've got the user, we've got the valid, and it also gives us a video timing out signal. And that video timing out reflects the horizontal, the data, the timing provided in the horizontal sync and the data and in the horizontal and vertical syncs and any blanking information. Once we have that stream, that AXI stream coming out, I've done the sensible thing that I thought would be sensible to do to help me achieve timing, and I've put an AXI for register slice in there. And then from that AXI4 register slice, I put it through a subset converter. Now, this subset converter, all I do in the subset converter is, what did I do? I did something. Oh, no, maybe I didn't. Maybe I put it in there, but I didn't do anything with it. But in some instances, you have to flick the RG, the green and the blue pixels around from what they are. So I included a AXI stream converter, subset converter, and then again the output of that subset converter goes through another register slice, just because I'm being paranoid, and then it goes into a small FIFO, and this small FIFO is just to make sure that if there's any slowness, any breaks in the parallel image processing stream. Then there's another slice, because I think I was getting exceptionally paranoid at this time. And then it goes through what's called a AXI4 video to parallel video converter. So this takes in the AXI4 videos in the stream, and it takes the timing information that's been set up that's within this video timing controller provided by the received video. And then it generates another parallel video, the parallel video going out. So if you're looking at this thinking, hey, Adam, why did you put this parallel stream in there? Couldn't you just have connected the DVI to the DVI? Then yes, you probably could. But if you wanted to actually do any image processing in the middle at a later point in time, no, you can't. Because it doesn't have the AXI image stream. And then the final block is a RGB to DVI stream, so that just encodes it into the TMDS stream for the HDMI display, such that the HDMI display can see what's going off. Now, this is a really simple design. The idea is you would drop in if you've got any image processing. Hey, no problem, Jose. Thank you very much for joining. And it'll be please check the recording. If you were doing any image processing, you wanted to, say, for example, do some noise reduction, some detection, maybe you wanted to do a Sobel image, so you do some edge detection or something like that, you could insert that on this image processing chain. You could insert that in this image processing chain here. And because it's all AXI stream at this point in time, you can just drop it in and go with it with no problem whatsoever. Now, the final bit before I stop for questions is invite us. So if you remember, we've got the microblaze in here. And what I did is once I built the example, I exported it to Vitus, created a platform. So we have a platform in Vitus, which has got the standalone microblaze in it, as you would expect. And then we have an application. And our application is a very simple application. All we've done is we've configured it to look up the configuration for the video timing controller. So the video timing controller is what is needed to generate it, is what generates the output timing for the AXI stream in to video out. And we need to set that up. Even if we're using the timing from the input video, we need to tell it that it's using the timing from the input video, and that's done via the software. And we also need to set up the GPIO such that we can drive the GPIO hot plug detect when we're ready in our software. So we pull this through, we configure the video timing controller lookup, we configure the AXI GPIO, we set the video mode that we're going to be operating in for the video timing controller. And then we set the source for the video timing controller as to where that's coming from. And then we update and we just allow the video timing controller to start both its detection and its generation. And once that's done, by the time it gets down to this point down here, you should see the image running and the image on the screen like we have, if I spin it around again one more time, maybe you can see it like we have in the demo down there where we can see my hand moving on. I'll move the camera down there in a second in a little bit. bit so you can see it a little bit more. And that is really how we create a nice simple image processing solution. So let's go back to the slides now. So the FPGAs, obviously, anybody that follows me knows this. Really, to be honest, the FPGAs are ideal for image processing applications because we can do everything in parallel. They're perfect for that. Actually, it's not difficult to get started doing with one of these. We can run through this quite easily and do this. We don't need to know VHDL or Verilog or even HLS or anything like that. We can literally pull the IP from the Vivado library, stitch them together, and then run it. And then often, this is the first step. This is just passing a simple image through from one point to the other. It's now up to you to decide what we want to do with that and why we want to do it. Maybe it forms the basis of an image learning application, a machine learning application. Maybe you're doing some more processing on it and working out like that. So I'll phrase that because this takes me to the end of the conclusion. So if anybody's got any questions, please pop them in the chat and I'll try to answer them. So Omar, you arrived late. Yes, the video will be recorded. It'll be on our YouTube channel, on my website later on. We set the timing inviters because if I just close this and come back here, the video timing controller, it has some on this control port here. It needs its register setting up for to tell it how to behave, and that's easier to do over using the microblaze than it is to write something to build that. So that works quite well. NASA, the white balance, edge detection, etc. Anything that you want to do like that, you would do at this point in the. If I can click on here. You would do at sort of this point in the image processing, you would drop in the IP codes that you've created in Vitis, from Vivado, from MATLAB Simulink, from Vitis Model Composer. You would drop those in and do that there. And if you take a look at my Hackster project, so the Hackster project I put up earlier on, if I just put that, I'll just put that in the chat again. If you take a look at that Hackster project, it will link you to it'll link you to my Hackster as well. And in my Hackster, you'll find a lot of applications of projects where we actually do put things like auto white balance in there, where we do put edge detection in there, where we do more advanced features on it rather than just how to create this simple initial image processing solution. Vivek, VDMA, yeah, where we use the VDMA to transfer to and from the DDR memory, typically on the processor, or maybe it's just buffered. You'll see if you go to my Hackster, you'll see an example with the AC701 where I think we use the DDR that's on there as a frame buffer and use that. There is DMA as well. You can use DMA if you want, just plain old DMA, because plain old DMA just moves things into and out of DDR memory, but it doesn't do it in like a line-based thing like you would need to pull the data out. So Andrew, you're saying if IP goes away, you need help with video coding from projects. So Andrew, actually, all of the IP cores in this example are all free. So there's not a paid IP core in any of these examples. They all come free. They all come with the base version of Vivado, and the MIPI CSI2 core is also free as well with the base version of Vivado. If you've got an FPGA that's got the H.264 codec in it, you can get all that up and running free. So Jan, this is a direct architecture because there's no frame buffer. Literally, what comes in, if you follow this path through here, it goes directly through a few buffers, but it goes directly out. So it just runs through and then directly out. Dennis, actually, no, I would recommend using the VDMA. If you're gonna put things into memory, there are 3 IP blocks you need to look at. There's the VDMA, there is the video write buffer, and the video read buffer, and they'll allow you to do it nice and easily with things. JB, you can find most of this stuff on my website, which is, I will put a link to it in a second, or you can follow me on LinkedIn if you're on LinkedIn. And that's generally where I put announcements of that. So my website's there. Bobus, considering how battery powered device, power consuming, considering camera image can be fully personal FPGA with options to organize myself. That's what I expect you to. I would expect, in terms of power consumption versus performance, you can get actually very, very good power, very good performance from the FPGA. And if you architect it right, you will also get exceptionally good power as well. But it depends upon what your constraints are. Someone asking, what if you want to implement the same in cars like Alveo U50, 55? It's identical. Identical. It's exactly the same. And that's one of the nice things that AMD have done. I know everybody always shouts about FPGA tools, but that's one of the nice things about the AMD ecosystem, the Vivado ecosystem, etc. is if you can design a microblade, you can design a Zinc. If you can design a Zinc, you can design an MP-SoC. If you can design an MP-SoC, you can design a Versal. And if you can do that, if you can, the design here, you can pick up and pop into a U50 or a U280 or something like that on an Alveo card, because the flow is exactly the same. Yes, it might be slightly different how you get the image in. Maybe you get the image in over from the PCIe, and then you do the processing in the PCIe, and then read the result back out of PCIe. But you can do that. Yeah, so somebody was saying, will the image run out of the box? It better do. If it doesn't, give me a shout, and we'll try and help you and get you going. My email address is on the front of the slides. It's all over the internet anyway. So just reach out and let me know if you can't do that, or if you have any trouble doing that. What other questions do we have? But yeah, I genuinely thank you for coming. You know, let me just put my camera down a little bit so you can actually see. So you'll have to excuse the mess of the office a little bit, but you should be able to see maybe the screen if I take it in there, which was it round. You see the screen, and we can see the camera if I look the camera around. So it's all there working quite nicely on the Kintex board. And it's been a very, you know, it's a very nice image processing solution to actually do. Pramod, it might be a little bit difficult for you to do it with a basis tree. Go take a look on my Hackster project, sir, because there are some image processing solutions where we use the basis tree, and actually there's one where we created a game, I think. So take a look on that. Dennis, what are you using for VDMA to DDR transfer? SoC, does that software look like on the Linux side? What VDMA do you recommend? So Dennis, we generally use the AMD drivers that come with it in Pedal Linux to support that. It's actually not that difficult to set up and get running. The best way to do it is to create the video for Linux 2 pipeline. And do it that way, and then all of that is kind of abstracted for you, and you don't have to worry about that. I know I keep saying go look at my Hackster, but there is, I think, a project on that where we did the video for Linux pipeline. And no, you can't. The Vivado IP is specific to AMD FPGAs, obviously, because I don't know if it's encrypted or not, but obviously it uses IP cores and macros and functions that are unique to AMD devices. So, for example, the DSP48 or the block RAMs or such like, it specifically calls up those which wouldn't have the same features or same availability or same mapping in other devices. It's a good starter board for video processing. Honestly, there's a nice starter board is the Avnet ZU board. That works quite well. A little tricky though for getting an image camera on there. The Krea, the KV260, the AMD Krea KV260 starter kit, that's ideal. That's designed for image processing, so that's a really good place to go. Yeah, the KV60s too. Oh, resource utilization details. Here we go. Design runs. So what have we got? 15,000 LUTs, 15,000 flip-flops, and I would guess the biggest one of those is the microblaze. So the microblaze is fairly small, 5,000 LUTs, 2,500 flip-flops. The MIG will be the next biggest one, the memory interface generator. Cornelius, I'm not sure what you're taking. I type those names, perhaps. Okay. Oh, do you mean the boards? So the AMD KV260 and the Avnet ZU board. And actually, it's the Tria. They've just renamed themselves Tria. It's the Tria ZU board. And they're really good. Actually, they're good fun to have a play with and to work with. And any suggestions? So I need to do some other webinars this year. You know, I like doing webinars. It's good fun to come and talk, even if you don't get the demo up and running right until a couple of seconds before go live because you're not thinking properly. But yeah, any suggestions for webinars? Anything you're thinking about? Anything you're stuck on? Anything you think you'd like to know more about? Either mention it in the chat or just give me drop me an email, drop me a message, and we'll see what we can do. So my email's on the front of the slides, but my email is engineering.com. Oh, and one thing I forgot to mention is we're hosting a conference as well in the UK in October, a one-day FPGA conference. So if you want to, there is a conference here. Can't type now. Called FPGAhorizons.com, and that's going to be a really cool one-day FPGA conference in the UK, and hopefully we'll make it and get one running in the US as well next year. So if there's nothing else, I realize we've run on a little bit. If there's nothing else, I will thank you all for coming so much, and I will end this now, and I will speak to you soon. Thank you very much. Bye-bye.